I feel bad. Good morning, everybody. Welcome back to Non-Euclidean Geometry. Plan for today. I got a new packet for you. We're going to be starting to talk about a new set of axioms we're going to be adding to the mix, which are Hilbert's Congruence Axioms. So we're finally going to start talking about definitions of congruence, start being able to talk about things like the distance between 2 points, those sorts of things. I've got my next office hours are on Monday after class, 2 to 3. Homework 4 still up, still due Wednesday. I decided we're not going to do a quiz this Monday, mainly because we just haven't really done enough since the last quiz, considering, especially considering we're starting something brand new today, and Wednesday's class was more of just a fun aside than something I'm going to test you over. So maybe we'll have a quiz next Wednesday or Friday, depends on my mood and how angry I get over the weekend. Any questions or comments before we get started for today? Oh yeah, I have to do this by now. Okay, so one day there's a psychology experiment where a mathematician, a physicist, and an engineer are all locked away in a room for 24 hours. And in their room, they're given a pencil, some paper, a can of food, but they're not given any can openers. They're not really given any way to open the can. So 24 hours goes by, psychologist goes in to check on each of them. First, they go into the engineer's room, where the pencil and paper are left unused, and the wall of the room is full of dents. And the engineer's eating out of the can. They just chuck the can into the wall over and over until it's split open. So the next psychologist goes into the physicist's room, where she has written a bunch of stuff down on the paper, and there's only a single dent in the wall. Turns out the physicist calculated the perfect way to throw the can into the wall and managed to get it open with a single throw. So finally, psychologist goes into the mathematician's room, where there are no dents in the wall. The paper is filled with equations. The can of food is still closed. The mathematician is nowhere to be seen. And there are some strange noises coming from inside the can. So the psychologist quickly opens up the can, and the mathematician pops out of the can saying, "Oh, thank you. I guess I got a sign wrong somewhere." Okay. So with that, I'm going to pass out today's... I know, most ridiculous. So here's the scoop. We talked about incidence axioms. We talked about the betweenness axioms and definitions and models thereof. We're going on to congruence axioms today. And just like how when we started talking about betweenness axioms, we still assumed that we had everything from the incidence axioms, same's going to be true here. So when we talk about our congruence axioms, we're still going to be assuming that our 3 incidence axioms hold true, and we're still going to be assuming that our 4 betweenness axioms hold true. It's just that we're going to add 6 more axioms into the mix. So we still have our 4 undefined terms from before: points, lines, incidents, and what does it mean for one point to be between 2 other points. We're going to tack on 2 new undefined terms, which is kind of the same undefined term that we're going to be using in multiple ways, which is the idea of congruence. So we want to have some idea of what it means for 2 line segments to be congruent to each other. And we're also going to have another undefined term, which is what does it mean for 2 angles to be congruent to each other. And that's going to be our undefined terms for the congruence axioms. We want to have some notion of what it means for 2 line segments to be congruent. And we want to have some idea of what it means for 2 angles to be congruent to each other. Can anybody remind me, what was like what was Euclid's interpretation of, how did he interpret whether or not two things were congruent? Jared?
It was the translational thing where you can pick one up and put it on top of the other.
Yeah, he sort of had this notion of superposition where two things are congruent if you can pick one up, move it on top of the other, and they match up perfectly. Yeah, we're not going to be using that. Because we already talked about why a lot of mathematicians have found that to sort of be a wishy-washy definition, something that they're not comfortable with. So when we look at our models later, we're going to see if we can come up with some better ways to define what it means for two line segments to be congruent, and then what it means for two angles to be congruent to each other. So here's a question. We're going to want to have some notion of congruence of line segments and angles. Why aren't we going to talk about what it means for two lines to be congruent to each other, do you think? Why would it maybe not make sense to talk much about whether or not two lines are congruent? Jack?
I don't know. If we use like our intuition for congruent, you could probably pick up any line and put it like on the, oh, yeah, any just like long line and put it on.
So any two lines will be congruent if we had some notion, you think? Megan?
Yeah, I was going to say that, and if you required lines to be in the same place to be congruent, then that'd just be the same line. Like, there's no endpoints to a line, so size-wise, they're not either.
Yeah, we're going to have some intuitive idea of two line segments can sort of be congruent or not congruent. So we may say, for instance, that these two segments would be congruent to each other, whereas these two segments intuitively are probably not going to be congruent to each other. This one you could sort of pick up, rotate around, place on top of this, and also they have the same length. Whereas this one, just no. Just no. So I would agree. I think, Jack, I like the way you put it. We're not going to have an idea of what it means for two lines to be congruent to each other because lines extend infinitely far in both directions, so you could always pick one up and put it on top of the other intuitively, and they'll always match up perfectly. And so every pair of lines would be congruent to each other, which means it would sort of be boring to think about line congruence. Whereas line segment congruence, line segments may or may not be congruent to each other. And ditto with angles. We could say this angle is probably going to be congruent to, I don't know, this angle, but not to that angle. So our ideas of congruence are mainly going to be focused on looking at line segments and angles. And for similar reasoning, I guess I should say, we're not going to talk about what does it mean for two rays to be congruent, because two rays would always be congruent. Questions or comments so far? So once we have a notion of what does it mean for line segments to be congruent, and what does it mean for angles to be congruent, which we're purposely not going to define yet, we can actually define what does it mean for other types of geometric objects like quadrilaterals and triangles and et cetera, to be congruent to each other using ideas of line segments and angles. So for instance, we're going to define triangle congruence now, where we can say that two triangles, ABC and DEF, are going to be said to be congruent if there exists a one-to-one correspondence between their vertices so that all corresponding sides are congruent to each other of the triangle. And we also want that all corresponding angles are congruent inside the triangle. So as an example, let's say we had a triangle that looked something like this. Let's see, this will be A, this will be B, this will be C, and then, sure. And close enough. So let's say we have these two triangles, and we want to say that these two triangles are congruent to each other. So what that means is we need to have a way to list out the vertices of each triangle, A, B, C, and vertices over here, D, E, F. And we want to find some one-to-one correspondence between these two sets of vertices, meaning a way to map the vertices of the first triangle to the vertices of the second, so that D, E, and F all get mapped to by exactly 1 point. And we want to do it in a way so that if we were to map, say, something like A to D and B to E, we would want it to be the case that the segment AB would be congruent to the segment DE. And if for instance, we mapped A to E and B to F, we would want it to be the case that AB is congruent to EF. So would anybody like to propose a one-to-one correspondence between the vertices that's going to make all the line segments and angles match up nicely? Joel?
A to F, B to E, and C to D.
Like that?
Yes.
Well, let's see. So now Joel proposed a one-to-one correspondence, and we should then check that does the line segment created by every pair of vertices here end up being congruent, and here we're going to use our intuitive idea of congruent for now. Do line segments made up of pairs of vertices here map to line segments that are congruent to their originals? So let's check with Joel's map. So AB, since A maps to F and B maps to E, do we know if AB is congruent to FE? Eyeball it and pretend Dr. Gerstle can draw perfect triangles. Great.
Oh, I was about to ask you to put little hash marks on the triangle.
Okay, fine. Here's how I intended this to look. I was going to do this after we did this, but fine. I'll do it now so you can see kind of what I intended. So, does AB congruent to FE? Line?
Yes.
Well, they both have a single little hash mark, so I would say, yeah, those are congruent. All right, Elaine. If Joel's one-to-one correspondence is to work, which segment would AC need to be congruent to?
FD.
FD, because A maps to F and C maps to D?
Yeah.
Okay. Jacob, are AC and FD congruent to each other according to my hash marks? Yep, they both have the triple hash mark. I tried to draw it so that these are both the longest side. So yeah, I would say that checks out. And then, Katie, what would be the last pair of line segments that we would need to check then?
BC to D.
Let's see, since B maps to E and C maps to D, we need to check if BC is congruent to DE.
Or
I'm going to put ED, but ED and DE are the same segment, so I'm just gonna choose to write it this way just to make it a little more clear how the one-to-one correspondence is coming into play. And Katie, are BC and ED congruent?
yes.
Both have the double hash mark, so yeah. So the line segments check out. In other words, Joel, I'm starting to have good feelings about your one-to-one correspondence in that pairs of vertices in this triangle that create line segments, the vertices that they map to, so like A maps to F, B maps to E, vertices over here that form the segment formed by vertices over here is going to map to a congruent segment over here. Any questions or comments? So Will, are we done, or is there anything else we need to check here to see if these two triangles are congruent?
I mean, I think with three sides together, they're pretty sure congruent. But we're talking about angles too, so we can check angles just to be sure.
If we were to have, say, the proposition side, side, side for triangles, we could say we're done, but we don't have that yet. So according to the definition, you would need to check for angles. So let's check our angles. Let's see. Well, give me an angle in the first triangle.
ABC.
All right, angle ABC. Brianna, what angle would ABC in the first triangle correspond to under Joel's one-to-one correspondence of vertices?
FED.
Let's see, A maps to F, B maps to E, C maps to D. Indeed. I'm sure you're all feeling fed up with this example. And are angles ABC and FED congruent? Looks like it. They both have the double angle symbol. John, can you give me another angle from our first triangle?
ACB.
Okay, where C is the point in the middle. Under Joel's one-to-one correspondence, what would that map to?
FDE.
Let's see, A maps to F, C maps to D, B maps to E. So does the angle ACB, is that in fact congruent to the angle FDE? I count three. Yes, they are congruent. Neato burrito. Sydney, what's going to be our last angle from the first triangle that we would need to check?
Oh, that's gonna be CAB.
The cab. And what angle is that going to correspond to vertex-wise? DFEs, let's see, C goes to D, A goes to F, B goes to E, F. Is this last pair of angles congruent to each other? Becca?
Yeah.
Indeed. That's going to be kind of the smallest angle in each triangle. So, it appears we have a one-to-one correspondence between the vertices of the two triangles, so that the corresponding line segments from one to the other all end up being congruent, and the corresponding angles from one to the other all end up being congruent. And so what ends up happening is these two triangles are said to be congruent because of that, because we could find a one-to-one correspondence that caused this to happen. It's not necessarily going to be true that any one-to-one correspondence would have worked out this nicely. Joel, I think you chose a really good one. But if we had chosen, say, A maps to D, B maps to E, C maps to F, if we had just gone straight across, for instance, I don't think it would have worked out so nicely. Because if A maps to D and B maps to E, we would have to ask, is AB congruent to DE? And the answer would have been no. So it doesn't need to be the case that every one-to-one correspondence makes the line segments and angles congruent, but there just needs to be a one-to-one correspondence between the vertices that causes all of these to happen in order for the triangles to be congruent. And if there's no one-to-one correspondence, no matter which one we checked, then the triangles are defined to be non-congruent to each other. If I were to define another triangle that was like that. Like that. Then, and if this was, I don't know, GHI, then no matter how we tried to form a one-to-one correspondence between ABC and GHI, the line segments wouldn't have checked out in terms of congruence, the ones that would have needed to be, and so we would say that those two triangles would then be non-congruent to each other. Any questions or comments? So the moral of the story is we actually have a well-defined definition for what it means for two triangles to be congruent. But in order for this definition to really have any meaning to it, we need to know, first of all, what does it mean for segments to be congruent, and what does it mean for angles to be congruent. Once we've defined these, then the definition of triangle congruence takes on a nicer meaning, but without those undefined terms, we have chaos, malarkey, if you will. I think made an interesting comment earlier, then that you said something like, oh, if the sides are congruent, then yeah, the triangles are going to have to be congruent. That doesn't follow strictly from the definition of triangle congruence, but it is actually going to be true from, and in fact this is a proposition we can prove, from our congruence axioms, once actually get to the congruence axioms, that if you know the sides are congruent under a one-to-one correspondence, it's going to have to be the case that the angles will also be congruent to each other. So yes, we are going to get things like side, 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 angle, 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 side. Yeah, I think that's the four. That will work as a result of our congruence axioms. Before we go into our axioms, though, I want to look at a little bit more of some definitions of things. Don't turn the page yet.
I did it before you said not.
All right then, Elaine.
No.
Would you say that your intuition tells you these two segments are congruent to each other?
No, sir.
Which one is smaller?
AB.
Why?
Because there exists a point E on CD between C and D such that AB is congruent to C.
See, this is why I didn't want you to turn the page.
I'm so sorry.
Yeah, in general, we can actually use our definition of our idea of betweenness to actually compare the lengths of two segments without having to arbitrarily assign numbers to them. Our definition of one segment being larger or smaller than another one is going to be that AB is smaller than CD if there exists some point E between C and D, with E in the middle of C and D, such that AB is congruent to CE. So for instance here, if we can find some point on the segment CD, I'm going to say about right here, we'll call this our E, where the segment from C to E is congruent to the segment from A to B, then we say that AB is smaller than CE, which we can write like this. And yes, you could just as equivalently say CE is bigger than AB. So this gives us a way to define a comparison between two line segments, being able to say which one is, quote, bigger, unquote, without actually needing to have any sort of like numerical measurement of their lengths. Instead, the idea of whether or not one segment is larger or smaller than another comes down to only the idea of betweenness and congruence of line segments. Basically saying, if we can cut CD off at a point in the middle, this point E, where the cut off piece is congruent to this other piece, then the whole segment from C to D is said to be larger than the segment from A to B. Oh, who do I want to pick on next? Megan. If AB is smaller than CD, is it possible that CD could be smaller than AB?
No.
Why not?
Because CD is greater than AB. If something's smaller, it's one or the other.
Is it?
Yes.
Do we have an axiom that says that? Go turn the page.
Unless you can say, unless you're saying smaller than can be equal to, and you're saying that E could also be B in the same spot, then no.
I see no reason why we couldn't also have a point between A and B, call it F, where AF is congruent to CD.
It's already smaller. You can't make it bigger.
Because it's smaller. You can't make it bigger. It just didn't make any sense.
Wow.
It's going to turn out to be the case that all, in other words, I'm sorry, Megan, I'm being mean to you. I really was being mean to you. But in other words, all of Megan's intuition is screaming at her that if AB is smaller than CD, it can't also be bigger than CD. But technically, we don't know that yet. We're gonna need to rely on some of our congruence axioms in order to be able to prove a statement like that, which feels very obvious that if one thing is smaller than the other, it can't also be larger than the other. But technically, that doesn't follow from the definition alone. Jared?
Oh, I was just gonna point out that the CEs for the smaller than and bigger than should be CDs, right?
AB, oh! Gadzooks. Indeed. AB is congruent to CD, AB is not less than CD. Or AB is congruent to CE, it's not less than CE. It's less than CD because of this existence of a point E between C and D. Yeah, good catch. Yes, Becca? What are you telling her?
But I was going to ask her the same question if you meant to have CD, but I didn't bother her.
Oh, how polite of you. So we can do something similar for comparing the size of angles.
I wanted to take the heat off of you.
I want the heat back on, Megan.
My goodness, such rudeness in this room.
You started it.
I'm not saying I didn't start it. But now look at you. Now you're like a child. Like, you started it.
This is not helping,
So we can also compare two angles the same way.
This is a toxic environment.
Let's say we have two angles, ABC, and let's say another angle, DEF. Very tempted to pick on Megan again, but I won't. Lacey, which of these two angles would you say appears to be smaller?
ABC.
Yeah, it looks like me like ABC is smaller, and not just because I drew the rays much longer over here, but because there's less space in here. And similarly to how we could use the idea of betweenness to help us determine, to help us compare the lengths of line segments without necessarily having to rely on numerical values for the size for lengths. We can similarly do something with betweenness to help us define when one angle is smaller or larger than another angle without necessarily having to assign like degree values or radian or gradient values if you're a crazy person. In which we're going to say that angle ABC, I'm going to give myself enough room, ABC, I'm going to say is smaller than angle DEF if there exists a ray which we'll call EG between ED and EF such that the angle ABC is congruent to the angle GEF. So in other words, if I can find some way to draw a ray in sort of inside of this angle that Lacey claims is the bigger angle, if we can draw a ray and make a new angle that's congruent to the original angle, then this angle will have to have been smaller than this bigger angle over here. So I'm going to try and draw my G. Yeah, that's close enough to a straight line. So let's say here's going to be the new ray I'm drawing, emanating from E and passing through this other point G, where angle ABC is congruent to the angle GEF. And so basically what we're saying is it's very similar to over here, where over here we said if we can cut off the bigger line segment at a point to get something that's congruent to the original, then this one is bigger than that one. Same sort of thing is going on here. If we can sort of intuitively cut off this angle to make it smaller, I put in air quotes because I'm not using small. I don't want to use the word smaller to define the word smaller. If we can cut this angle off here to get something that's congruent to the original angle, then this angle, angle DEF, must have been larger than the angle ABC to begin with. And that's going to give us another way of, similar to what we did for line segments, to compare the size of two different angles. Yes, Jared?
Do we have an axiom for ray betweenness?
Oh my goodness.
Angle, yeah.
Have we talked about what it means for array EG to be between array ED and EF? Good question. I was about to ask you all that. We technically haven't defined that yet. I think we can define one there pretty quickly. We can find one there pretty quickly by saying we could say I think that ray EG is going to be between ED and EF if the segment DF happens to intersect the ray EG. So we could say something like EG is between ray ED and ray EF if there exists some point, we'll call it H, on the segment, on the ray EG, such that H ends up being between D and F. Would be how I would define one ray being between two other rays. In other words, if the segment DF happens to intersect the ray EG at some point, then we can say that the ray EG is between the other two rays. That's a good observation, Jared, and I'm glad you noticed that while we may have all sorts of visual intuition screaming at us that here EG is between ED and EF, that was something that we never actually defined, what it means for a ray to be between two other rays. So it's good to have a let's see, an unambiguous definition that we would be able to work with, or something like this. Any other questions or comments? I'm not going to write these down on the board because they're in the packet, and well, you all have visual intuition as to what acute and obtuse angles are. But we're going to say that angle ABC is acute if it is smaller than a right angle, and angle ABC is obtuse if it is larger than a right angle. Waiting to see if Jared raises his hand to point out something we're missing when we define acute and obtuse in this way. Jack?
Do we have to redefine right angle?
Oh, technically, well, we can define a right angle. We can define I'm not going to write this down on the board. A right angle is defined to be supplementary to it, or it is an angle that is congruent to its supplementary angle. Same way that Euclid defined it. But something else is missing when we define acute and obtuse in this way. If it is smaller than a right angle, or obtuse if it is larger than a right angle. Joel?
We never defined what larger means.
Well, okay, swap DEF is larger than ABC in this first line, and that gives a definition of larger. Here we just assume that DEF is larger than ABC if ABC is smaller than DEF. Megan?
I'm not sure if this is just semantics or not, but an obtuse angle doesn't really work if it's like 270 degrees. If it's larger than 2, you're just looking at the smaller acute angle at that point.
Assume all angles are...
Like less than 180 degrees.
Assume we're only looking at angles less than 180 degrees. Okay. You all are pointing out valid things, but you haven't touched upon the thing I'm aiming for yet. Sydney? We never said that all right angles are congruent to each other. Yeah. Euclid assumed that as a postulate, as one of his axioms, but we have not. And it turns out that is not going to be one of our congruence axioms. We are not going to have an axiom of congruence that says all right angles are congruent to each other. We're not going to have it as an axiom. We're actually going to have that as a proposition instead. But yes, that's a good observation, Sydney, in that if we want to be able to have a term like this angle is acute if it is smaller than a right angle, that's not really a very precise definition unless all right angles are defined to be equal to each other. It wouldn't be a good definition if it's like, oh, well, it's smaller than this right angle but larger than this other one. So if we want it, unless we want to have a specific right angle in mind when we're talking about acute versus obtuse angle comparisons, it needs to be the case that all right angles have to be congruent in order for it to not matter what angle we're using as our measuring stick, so to speak. Jack, I think you had your hand up earlier.
Yeah.
Is that what you were going to say?
Yes.
And good observation. It's going to turn out to be the case that under Euclid's axioms, all right angles are congruent was an axiom, but in Hilbert's system, it's going to be a proposition, which we'll see later on. All right, enough stalling. Time to give us our axioms of congruence. And this time, there's so many of them that I had to spread them out over two pages. So some of these I hope are going to be pretty non-controversial things that feel like should be intuitively duh, based on how your ideas of angle and line segment congruence should work. One of these is going to be a little bit more spicy, in my opinion. So let's start with our first congruence axiom, which is if A and B are distinct points, and A prime is any point, then for any ray R emanating from A, there exists a unique point B prime on R such that AB is congruent to A prime B prime. So what does that mean? So it means suppose we have a line segment AB to start with. AB, and we have some ray, and we have a ray, which we're going to say is emanating from some point A prime, and let's say it goes off that way. So what this is saying, the first congruence axiom, is that we should be able to find some point on this ray, and we should be able to find a unique point on this ray, which is going to be about here, such that if we cut this ray off at this point B prime, then the segment A prime B prime should be congruent to AB. So in other words, given any ray and any sort of fixed distance that we might want to cut the ray off at, there exists a unique point on this ray that we can cut the ray off there, and what's left is going to be congruent to this other segment that we started with. It's basically rays, there's a unique way to cut any ray off to have a fixed length, would be a kind of an intuitive way to say that. There exists a unique way to cut any ray off at a fixed length. Garrett, I think I heard you making some noise. Do you come to a realization?
Oh, no, I just got it. I understand what it's saying.
Neato burrito. Any questions about this one? Hey?
Is this basically saying you can construct, I mean, not that it's like more abstract than that, but you can construct a line segment of any length?
On a ray, yeah. It basically saying if you have this ray already, and if you have your measuring stick already defined, the segment AB has to already exist, then you can cut your ray off, snick, 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 so that what's left is the same length as your measuring stick.
All right.
But AB has to already exist, and your ray has to already exist in order to be able to do that. This axiom is not the spicy one. I don't know. It's interesting, if you ask me, but it's also one that feels like, yeah, duh. If I had some length 1 in mind, I wanted to say, can I cut this ray off to make it a length of 1? Then yeah, there's probably a unique point that you can choose to do that. The point that's 1 unit away from the start. Let's go to the second one. Second one is one of Hilbert's famous Cheedy two-parters in a single axiom. Which is, given any segment AB, first of all, we can say that if AB is congruent to CD, and AB is also congruent to a segment EF, then CD has to be congruent to EF. So in other words, if you have two segments that are congruent to the same thing, then they also have to be congruent to each other. And as a part 2 to that, AB is congruent to itself. If I were Euclid, I could say, I can pick that line segment right off the page and put it right back down again in the exact same point it started at. Same points it started at, I should say. This one is not the spicy one. It's another one that feels like, duh, Dr. Gersel. But if you have two segments that are congruent to the same thing, they're also congruent to each other, and every segment is congruent to itself. I hope neither of those are too mind-blowing. Everyone okay with that one? Thank you for not making me draw a picture. Congruence Axiom 3. If, hey, I said 3. If B is between A and C, B prime is between A prime and C prime, AB is congruent to A prime B prime, and BC is congruent to B prime C prime, then AC is congruent to A prime C prime. So obvious, why would anyone need a picture? Let's draw a picture. So basically what this one is saying is, suppose you have two kinds of, you have two lines going on here. One where we have points A, B, and C. That are all collinear. B is our point in the middle. And we have another segment going on. A prime, C prime, B prime. So what this is saying is if we have these two sorts of segments going on like this, if the AB piece is congruent to the A prime, B prime piece, and if the BC piece is congruent to the B prime, C prime piece, then the entire segment from A to C has to be congruent to the entire segment here from A prime to C prime. Intuitively, if you take two segments of the same length, say AB and A prime B prime, and you tack on to the end of those new segments that are also of the same length, BC and B prime C prime respectively, then the big segments from A all the way to C has to be equal to the segment from A prime all the way to C prime. So in other words, adding like segments to like segments gives like segments. Dr. Ursula, why are you using the word like instead of congruent? First of all, because like is shorter than congruent, and I'm lazy. Second of all, I'm trying to phrase this to look very similar to one of Euclid's common notions, which is like added to like produces like. So like if we were talking about numbers, we could say something like if A equals B, and A1 equals B1, and A2 equals B2, then A1 plus A2 equals B1 plus B2. Saying the same basic thing, except this is for numbers, whereas this is for line segments that we're adding together. Is everyone okay with this one? This is not the spicy one. Speaking of spicy, all these three axioms we've had so far only have to deal with line segments. None of these have anything to do with angles. Congruence axioms 4, 5, and 6 are all angular in nature. But for that, we will have to continue on Monday. So on Monday, we'll talk about Hilbert's 4th, 5th, and 6th congruence axioms, including which one's the spicy one. And then we'll start looking at some models and some propositions relating to how can we use the congruence, betweenness, and incidence axioms all together. After these last 6, we'll have 13 unique axioms to work with.
Yeah.
Have a good weekend, everybody. See y'all on Monday.